starting over. Given the root node of the binary search tree, BST, and a value, you need to find the node in the BST that the node value equals. The given value, return the subtree rooted with that node. If such node doesn't exist, you should return null. For example, and the value to search is 2, so you should return. Oh, you have to return that whole subtree. Oh. Since no node by, we should return null. You would see next way to have a tree format, not null. Okay. So basically, what we're doing through searching binary searches. So if the value is larger, so if it was like 5, we would have to go to the right. If the value, and then once we go to 7, we say we go to the left, but then we would end up with nothing. So to me, it seems pretty basic. You're just basically using the binary search trees, using that structure. If you're looking for 2, you know you're supposed to go to the left when you start from the 4. So you just have to look at the value that you're currently at, and then go to the left, or go to the right. And that's what I can do here. So we'll do with a while loop first. So we'll say the val is the val we're looking for, right? Okay, so while root, basically. And then what we do is if val equals if root.val equals val, then I will going to return that's this current root. If root.val is less than val. If it's less than val, you have to go to the right. Well, let's do if root.val is greater than val, then you'd go to the left. So then we say root equals root.left. If root.val is less than val, then you would go to the right. I guess if you don't find anything, you just return. What are you supposed to return? Just return null. So I don't know when they say when you do you return none. I'm not sure we're supposed to return when it's none, but let's just run code and we'll do an example to see what they expect. It says that the empty tree is represented by null, therefore you would see the expected output serialized tree format as this. Okay, sure. So you return an empty thing. Okay, so this was accepted, but what if you have 4, 2, 7, 1, 3, and you're looking for 5? Oh my god. It has to be a OPA. Maybe you just return the root. Well, I guess you do return that. But now that I think about it, you would also just return the root, because the root would be equal to none if it searches all the way through. Yeah, okay, so that should work. It works for the case if it doesn't exist. I mean, I could come up with another one. Let's see, you're looking for 7. And then also suppose you're looking for 4. I don't know what happens. Let's see. This is expected and accepted. So yeah, that pretty much does it. I think that'll work. And now, since that worked, let's try to do this with recursion. So let's mark this down. This is one solution. Delete that and put some here. Okay, so that's one solution. Okay, one solution would be basically say if not root, then or this, or if not root, return I guess. If root dot val equals to val, then return this root. And the basic search mechanism is you go to the if root dot val is less than val, you want to call search est. I forget if you need to put self in front. I think you do need to put self in front. Self search est with this is if root dot val is less than, so that means if it's if the root value is less than the value, you need to go to the right side because you need to increase the root dot val. So we'll go root dot right, and I guess keep the val. If root dot val is greater than val, then go to the left. Okay, I think that's it. Then code. Okay. So what happened here? Okay, so let me think about this. So if root dot val, so if we're here at 4, right? And we're like, well, hey, 2 is less than 4. So I would say go to the left. Here what we say is, if my val is smaller, so let's say I'm searching for 7. I say, well, my 7 is larger than this, so I want to go to the right. That's weird. It's not root. Okay, let's print out root to see what path it takes. Alright. Okay. That's all I can print out, I guess. So you get val 4 left. Okay. So then you go to this. So you go to the 2, right? So you have the 2. All of these. But the root dot val should be 2 here, right? So it should be equal. So it should can I print out dot val? Because 4. Oh, that's true. I can probably read dot val after it already checks this condition. For 2. So oh, you know what the problem is? I always forget this, dude. I need to return from these. Yeah. I always forget. I oftentimes forget to put the return. But yeah, I want to return this value. So anyways, this is accepted. Small mistake there. So I'll submit this. It passed all this 4 tests. And that was accepted. And if you want to analyze the runtime, yes, runtime's a little slower with so it looks like the runtime is slower with recursion. The memory required more memory with recursion, probably to memorize the whole stack. I guess stacks don't get too big in this problem. But yeah, so yeah, that's pretty much it. This is a good problem to practice, a very basic problem, just searching through a binary search tree. Very starter algorithm, I feel, like a textbook algorithm. Definitely, I remember doing this in class.